Hi, so this video is in follow-up to the video here in this card, which covered the fundamentals of type actions and force curves. Now, basically, turns out that this whole time it had actually made a rather big mistake in how I was generating those force curves and interpreting the data. So basically, let's, first of all, again, I'm always using Algodo here to make these simulations. What was happening was, basically, so you can see here now the force curves being generated. Yeah, well, my keyboard is a Model FAT. Anyways, so originally I was getting this graph over here, just this graph, and I was seeing a negative force, and that to me just seemed wrong, or it seemed unintuitive compared to what I thought I was feeling in the key press. So I basically went ahead and switched to using this magnitude, which I thought looked correct, and I was assuming that this cusp here was representative of the point at which this here was contacting my simulated behind segment universal bar, but this was completely wrong. So pretty much I was wrongly assuming that this force that I was plotting, based on this simulated finger, was the same as the normal force that this key was exerting on that finger. But actually, this is measuring the net force. So that means the sum, so the vertical component, y component, the sum of the normal force, the positive normal force, and the negative or downward force of gravity, so that would be constant, as well as the constant input force that I'm producing with this thruster. Like so. So that means that pretty much I should have been solely relying on this original net force graph. So now looking back at our Olympia SM-4 force curve, this is the correct interpretation. So basically then, this here is our normal force, but translated down by the constant force of gravity and the constant input force. Given that, as light as this particular typewriter feels to me, the force should actually be increasingly increasing. So that means that the rate, it's increasing, but at an increasing rate. Which was kind of unexpected, but I guess the whole idea is that, yeah, it's hard to really notice because my particular SM-4 has such a light touch. Now, as in the original Olympia or Roy typewriter video, in this video card, from which I originally referred you to this video, I was looking into, or mentioned, how my SM-4 has a much lighter touch compared to earlier Olympias, or earlier type actions. So basically, the difference that I had noticed was that compared to the earlier Bellcrank, at least for these longer or bottom row keys, the angle of this arm here was decreased. Same thing here. This angle was brought down a bit, while everything else was virtually the same. Though, as you can see here, yeah, the Typebar did change in shape, but turns out that that minor change in geometry was in fact sufficient to get rid of the original heavier or tactility, like a tactile bump. So now I'm going to simulate this. So you'll see that now there's actually an initial bit of a drop, then a sharper increase. So this feature here in these force curve graphs is something that I tend to associate with quote-unquote tactility. So now let's compare this to quite the exemplar of tactility, which is the Torpedo type action, namely the Torpedo 18B. Now I did recently learn that the Torpedo 20 and 30 used a different type action. And 10 years before that, was the original, well, at least the last usage of the Torpedo 17 type action, which originated with the 30s Torpedo 15 type action. But yeah, now we're going to focus on this version, which was, yeah, basically ran throughout the entire Torpedo line, starting in the 30s, so late 30s and early 40s. So you can see here that we basically have the same but greater drop. And in this regard, now yeah, beforehand, when I was relying on the magnitude, I was getting this here, which I would have likened as being a kind of tactile curve, more akin to basically the rubber domes of typewriters, but as you'll see, the actual representative of this is a different type action, namely the Underwood-style type action, which I'll show later. So yeah, that's that. Then we have another instance of this style of force curve as seen on my Patria typewriter, in this case a 50s Byron portable clone of the Patria design. So in this case, the force initially decreases in a kind of linear manner, but we then see that it's really, for the most part, parabolic, if not catenary. And yeah, here it's a lot rounder, even more bowed, but not as steep as on my Torpedo. Then we have the Commodore Speedwriter, or earlier Consul 15 series portable type action. And again, I'd already shown you in the previous video that this is a true example of a constant force at the start, but instead of it decreasing increasingly, as in the incorrect interpretation, it's actually supposed to be increasingly increasing near the end. Likewise, we have the Triumph-Adler Perfect, or just the general Triumph-Adler portable type action, at least prior to the 70s, and excluding the Adler Privat. And you can see here, actually initially gets a bit of a, like, decreasingly increasing force. Then we have an inflection point around halfway, then it increases. Yeah, that bump there is from my simulation of the behind segment universal bar. So beforehand I made the incorrect assumption that you would have had the mirror, so I thought that that was the cause of the high tactility that I was feeling under my fingers, but actually the real tactility is from this curve here where it gets almost flat. So it's this high change or decrease in the rate of increase of the force on your fingertip that is creating the tactile feel, or the sharp tactility of this Triumph. Now, what I found surprising is that that style of force curve from that Triumph is actually quite similar in form to that of this family of type actions, namely those that use class 3 Bellcranks. So before that, let's first do some nomenclature. So basically, for your levers, class 1 means that your effort is over here, while your load is over here. Class 2 means that your effort is over here, but you are connecting a link, for example, over here. And that means that, yeah, this is your load that will pull on something else. While class 3 means that we've moved this over here instead, and we're applying the load over here. So now, what I define as a bell crank is basically, technically, any subset of lever where either the arms here, the effort and load arms, are not collinear, or the effort and load arms, or rather the effort and force vectors, are not parallel. Now, in the first special case, if we have a collinear, or initially what you would regard as a class 1 lever, but the effort and load force vectors, so here and here, are not parallel, then I would technically consider this to be operating as a kind of bell crank, since it is changing the direction to which the input force is being applied at the output. And then, given that, for your bell crank, in order to determine its equivalent lever class, my method, which I've determined, is to take things with respect to, these here are kind of misbehaving. Yeah, to take things with respect to the effort arm. So basically, let's say that you have an effort vector like so. We want to take the projection of the other two vertices here, namely the fulcrum vertex and the load vertex, onto a line perpendicular to our effort vertex over here. So that means then that the class of your bell crank will be based on the class of the collinear lever on this projection here. So if the order is effort, fulcrum, load, then that's class 1. But if, for example, we were to rotate this bell crank like this, and our effort was over here now, while our load is over here, we end up with effort, load, and then fulcrum. This is a class 2 lever. So I would call this as operating a bell crank operating in the class 2 function. And then finally, over here, if we position it like this, we now have the order of fulcrum, effort, and then load. That would mean that if our effort force is pulling like thus, this is operating in the equivalent of a class 3 lever. So I would call this a class 3 bell crank. Then we have the edge cases, where if our effort is parallel to the load arm, I would call this a class 1.5 bell crank, since it sits between being a class 1 bell crank and being a class 2 bell crank. Then, in the case that the effort vector is parallel with a line between the effort and load vertices, I would call this a class 2.5 bell crank, since the bell crank is between being either a class 3 or a class 2 bell crank. This classification would be the exact same regardless of the shape of the bell crank. So in this case, if we have like a 90-degree bell crank here, then if our effort arm here is parallel, like so, then we can still call this a class 1.5 bell crank. But if the angle changes like this, then it becomes class 1. Then we may eventually reach this point, like here. That would be a class 2.5. Since we are at the brink between either a class 2 arrangement or a class 3 arrangement. So this is our effort, this is our load. The same goes for this Bellcrank, which here has an acute angle. So say that our effort is over here. Right now, it's class 1, but if we rotate this, or more so, we are rotating the effort vector, then, okay, well, this here, if the effort is parallel with the effort arm, then that is a degenerate case, where the effort isn't capable of actually causing any torque. But on the other hand, if we do have the load arm being parallel with the load force, as we know, this arm will still be able to apply a sideways torque to that output arm and eventually also impart an upwards component force. Anyways, regardless of the direction of the actual load force vector, this here would still be a class 1.5 lever. So between class 1, class 1.5, class 2 now, and then eventually over here it will be class 2.5, and then class 3. Given that, I will now claim without rigorous mathematical proof that for all Bellcranks of any shape, that is, with an effort and load arm of non-zero length and that are not collinear, there will always exist an angle for the effort vector corresponding with any one of the 5 Bellcrank classifications, namely 1, 1.5, 2, 2.5, and 3. Then, for levers or Bellcranks where the effort and load arms are collinear, the class of that lever or Bellcrank will be invariant, that is, always the same. So if it's class 1, it will always be class 1. If it is class 2 or 3, it will always be such, regardless of the angle of the effort vector. Lastly, if the effort and load coincide, we'll simply call this a link instead of lever or Bellcrank. If within our reference frame one side here is fixed, then we can call this a fulcrum, and we can have either the effort or load both on this part. Now, technically, in the case that it is merely providing a circular motion constraint, then the concept of effort and load don't really apply. But in the case that this thing that we previously called the fulcrum is actually moving with respect to another frame of reference, then we can regard this, or either end, as being either the effort or the load, and then there would be no more fulcrum. Also, in the case that we have a Bellcrank-shaped rigid constraint between 3 points, but the effort and load are parallel, then I would be more reluctant to call this a Bellcrank and would rather call it a special case of lever where the kinematics of the effort and load vertices are different than on a conventional lever. With that, you can see that all these type actions make use of class 3 Bellcranks because of this pivot order and the respective direction of the effort vector being appropriate. And, of course, these key levers here are class 2. Now, given that, if you want to measure the force curve, and again, we want to compare this to that of the Triumph or Adler type action. We may be surprised that this style of type action actually produces a result quite similar, as you can see. Though, as you can see here, the inflection point is probably a bit steeper compared to on the Triumph, so that might explain why, like personally, when I type on an Olympia SG-1, it doesn't feel nearly as tactile. It just feels more so smooth, or I mainly only really feel like this part, not so much this bump here. Then we can compare this to the Underwood SX. I believe either this, so yeah, like in the Underwood type actions, I'll after this show you the earlier style of Underwood type action. But yeah, there was at least one other design iteration before this one. So yeah, this is based on this link here. So you can see that, yeah, it's a lot steeper, and the part where the force becomes a bit increasingly increasing is kind of truncated. So that characterizes the, like, what I call flat and full touch. And it so happens that this is actually quite similar to the touch of my Smith Corona 88 Secretarial that was featured in this video here. So yeah, class 2 lever here. Then if you take this effort arm here, that, yeah, this would technically be a class 2 bell crank. Anyways, that eventually pulls a class 3 bell crank for sure. And our force curve will be very similar. And indeed, in real life, I find that these two machines feel quite similar, though this Underwood has a slightly heavier touch. Now we visit the Underwood-style type action. Now, this was technically roughly based on my Halda 12 typewriter, which is basically an Underwood clone in terms of its mechanics, but you will see here that it produces a pretty interesting force curve, which again I would regard as being the analog of rubber domes, but in typewriters. So you can see, basically get this round, pretty much the complete opposite of the Torpedo touch, but it still feels tactile, just in a different way. So increasing then decreasing, as opposed to decreasing then increasing. And you can also see here, so this is the speed of the finger tip with respect to the displacement, and I believe that that does also have a bit of an influence on how you perceive the touch of a typewriter. So there's a kinematic aspects, and there are the dynamic aspects, or the force aspects. So yeah, pin and slot type action. This is still class 2 lever. This is still a effort. Yeah, that would be, yeah, class 1 bell crank. And this operation here, if we regard the weight over here as the load, then this is still class 1 actuation of this type bar. Here we can return to my rough simulation of the Corona number 3 type action. So now we have class 1 key lever, and then class 3 actuation of the type bar. And yeah, I compared that to the force curve of the Torpedo, though as you can see, instead of it being more close to parabolic, we're a bit askew, where it goes like this and then kind of linearizes. Then we can quickly look at the corrected force curves for these machines. So Fox here, again, let's compare that to the original incorrect stuff from that video. So originally I thought that it was this kind of tactility, but the reality is it's this kind of tactility. Again, in this case it so happens to technically be similar to the early Olympia Portable, but in reality there are certain differences, like, again, I would more so describe the Fox as feeling like cloudy or more full and bouncy. Same idea here for the Monarch, which again, from the original video, has a very similar but slightly different style of doing virtually the same thing, and it indeed ends up with roughly the same force curve. Oops. yeah, same force curve, but in reality, my Monarch happens to have a really light touch. Now I can also show you the Smith Premier 60, so that's covered in this video here by Will Davis, where it's the exact same thing, but the bell crank has been turned around in order to allow them to use a segment. So in a segment, you can't have a pull to front type action, so instead they are pushing from below. And we'll see, and indeed I can confirm in real life, that those two machines do actually have a different touch. So technically, the Smith Premier here shares more in common with the Corona number 3 force curve because of its going like bowing and then kind of linearizing. Then I recently was able to find a photo of the type action of the Titania. That machine I originally wrongly compared to the LC Smith. Turns out that it actually has a completely different type action using this pin and slot system, and that will yield this kind of force curve. So initially starts, yeah, that would probably be pretty interesting. Much smoother, kind of slight tactility, and then increasing. Then we have our LC Smith, at least my best interpretation of it. And yeah, that's purely increasing. So technically the opposite kind of force curve compared to the successor, the SC-88. So yeah, this type action was actually used all the way from the earliest LC Smiths to the Speed King typewriters, and then with the 50s Smith Corona 88, they redesigned the type action to what I showed you earlier. Anyways, now we have this rough Visigraph based on Will Davis's stuff, or video, and article. Again, because of the shape of this bell crank, it seemed like, well, yeah, the position of those pivots might not be perfect, but it might be similar to an Olympia touch. Well, in this case, technically, a lot smoother of an increase. Then we have the Remington number 10, which so happens to have one of the most linear of these force curves, as you can see here. Now over here we have my rough simulation of the Adler Privat type action again, based on what I've seen from photos as well as video of this machine, and of course my now more recently owning an Adler Privat. So class 2 key lever, but now we instead have a class 3 bell crank system. And it so happens that that force curve is in fact similar to that of the SG-1, which again is supposedly similar to the force curve of my Triumph portables. So initially decreasingly increasing, and then increasingly increasing. Technically, yeah, it's weird because from this simulation it would seem like I would expect the Adler Privat to have a more tactile touch than my Triumph portables, but here, at least in real life, it actually is in fact the case that I find my Adler Privat to feel basically just like an Olympia SG-1, but with a lower inertia in the type action, and a slightly more shallow touch, so like the keys don't press as deeply. one last metric is that we can measure the angular velocity of this type bar with respect to time. Now, ideally I would also be able to measure it with respect to the finger or key displacement, but unfortunately in this game I can only plot variables of the exact same object, in this case, this guy. But anyways, so you can see here the rate, the angular velocity is generally increasing in magnitude by a constant rate, and this is the case for most of the type actions that I've simulated, except for for example, that Underwood type action, where instead of having a bowed speed curve, or speed with respect to displacement curve on your fingertip, we have that cusp here. That leads to a bit of a unevenness or slight wavering in this rate. But now, given that, if this is basically the same, like kinematically, across all these typewriters, then of greater interest is what happens after the release of the key. So in this case, so this game does allow you to represent the coefficient of restitution, or basically how much energy is lost in the type bar after it hits the platen. And here we can see that there's a mild increase in force. And now, with these simulations, can't really consider this to be the most accurate. Of course, like at full speed. Basically, when I'm tuning these springs here, these return springs, I only do it so that it looks like the action is reasonably realistic or operating in real time. Now, comparing to this Triumph-Adler Perfect, that's excluding the feature where the escapement basically is able to kind of apply a bit of a pushback on the type bar to make it return even faster, or to an extent kind of increases the coefficient of restitution of the platen. So again, linear, but now we can see initially higher, and then here it kind of bows off. But yeah, the point is some machines seem to be able to, at least in simulation, return the type bars more quickly. So now let's look at the console. And again, you can also notice these curves. So yeah, again, this curve generally doesn't really matter between machines, other than its minor contribution to what the typewriter actually feels like. So again, mostly pretty straight, constant acceleration of the type bar, and here it's constantly increasing, it seems. Though I personally find that other factors of the force curve, such as the initial touch weight, can influence how fast you're able to type, or basically control the keys. So sometimes maybe the type bars do return quite quickly, but other factors make it more difficult to actually make them do so. So like how quickly you're easily able to release the keys and remove any possible resistance to the resetting of the type bars. And then finally, you can look at the Olympia. And if you know the length of the type bar, you can use the angular velocity here to also normalize the thruster or touch force, the constant force here, and your spring velocities if you want to end up with more equivalent or directly comparable force curves. So yeah, again, basically normalizing the impression strength or speed. But otherwise, I'd say it suffices to be able to just compare the shape, the general shape, without everything being perfectly to scale. So yeah, with this Olympia, at least in simulation, it seems like the return speed should be increasing. Then we have the Olympia SG-1. And here it seems mostly constant, maybe slightly decreasing near the end. Then we have the Underwood SX. Yeah, so interestingly, for this particular machine, we do have a bit of wavering. And yeah, generally decreasing a bit before landing. And then the Smith Corona 88 Secretarial. Also a bit wavering. And yeah, pretty similar. So, I mean, if this actually were happening in real life, then in theory that might limit the speed, or maybe this might actually kind of aid the speed. I personally wouldn't know, but like basically the point then is that you might be able to think of these angular velocity curves as characterizing the kinematics of typing on a particular machine, and pretty much some kinematics may be more optimal for fast typing than on other machines. So basically how easily or effectively it is that you can sequence multiple parallel keystrokes without the type bars colliding. Alright, so if you found this video interesting and would like to see more quantitative evaluation of typewriter designs, feel free to like and subscribe.